Hello everyone, I'm Farindra Tejavi from NITPY. I'm going to explain about half adder and full adder today. Today we'll discuss about the truth table, circuit diagrams, and logic expressions of half adder and full adder. Introduction to adders. Adders are arithmetic combinations circuit used in arithmetic operations. They perform simple binary addition of one bit, and multi-bit also is possible in half adders, which we'll discuss in the upcoming presentation. There are two types of adders, mainly half adder and full adder. They're commonly used in digital systems like ALUs, arithmetic logic units, as I previously told. It's useful in binary addition of two-bit numbers or single-bit numbers. Moving on to half adder, it's defined as a combinational circuit that adds two single-bit binary numbers A and B. By meaning combinational circuit, I mean to tell that there is no dependency of the memory element here in the circuit. There will be no memory element in the circuit, and the current output will depend only on the present input. It doesn't depend upon the previous stored input or previous stored output. The outputs of this half adder would be sum, which would be XOR of A and B. For carry, you get AND operation between A and B. We'll discuss it in detail in the next slide. The truth table for half adder is one second, I'll explain this in detail. Input A and B are given to the half adder. Now, when you add 0 plus 0, you get 0 as a sum, and carry would be again 0. Now 0 plus 1 again would give you 1, and the carry would be 0. 1 plus 0 is again 1, and carry is 0. 1 plus 1, like I'll explain you this, right? 1 plus 1. Now here you would get 0 as the sum, and 1 will be the carry. Now again when 1 will go down, you will get 1, 0. So 0 is the sum, and 1 is the carry. If you understood this. The block diagram for half adder is you draw a rectangular box and you provide it two inputs A and B in the case of half adder, and you get two outputs which are sum and carry. Coming to the circuit diagram of half adder, we'll implement this using two inputs A and B. You pass A through AND gate, and using NOT gate you pass B complement, so that you will get the AB complement, and similar way you get B and A complement using another AND gate. And this is used along with the AND gate so that you get the OR operator in between them. This expression is nothing but the A XOR B, which can be derived using the Boolean expressions or Boolean laws. And this could be simply implemented using the XOR gate, like by just giving two inputs A and B. You will get here A XOR B. This is also a right form. There's no wrong in it. And next, you pass A and B through the AND gates, and you get AB, which is just the carry. Now coming to full adder, it's also a combinatorial circuit that adds three single binary numbers. As we discussed in previous case for half adder, it's just two single bit binary numbers where you add A and B, and you get A plus B, and you get a sum and a carry element. Here in case of full adder, you add three numbers A plus B plus C, and you get the same sum and carry as outputs. Now the sum output expression for sum would be A XOR B XOR C, and for carry it's AB plus BC plus CA. We'll discuss this in detail in the coming slide. Full adder truth table. I'll explain you this in detail. 0 plus 0, when you give input, you will get 0 as output. And when you add 0 to the C input, you again get 0. Now coming to next one. 0 plus 0 is 0. 0 plus 1 would give you 1, and carry is 0. 0 plus 1 is 1, and 1 plus 0 would give you 1, and 0 is carry. 0 plus 1 is 1, and 1 plus 1, which we discussed in previously, 1 plus 1 would give you 1, 0. So 0 is the sum, as you saw here, and 1 is the carry. 1 is the carry. 1 plus 0 is again 1, 1 plus 0 is again 1, and carry is 0. 1 plus 0 will give you 1. 1 plus 1, I told you, 1, 0. 0 is the sum, and 1 is the carry. 1 plus 1 will give you 1. 1 plus 0, now it will give you 0, and 1 as the carry, as I told you in the previous class. Now let's see the third one. 1 plus 1 is 1. And again 1 plus 1 you're doing. So you get here 0. The carry would be 1, right? So 1 is the carry element. Now you have here 0 plus 1, which will give you 1. 1 is the sum and carry is again the same 1. Hope you understood this truth table. The block diagram for full adder would be again a same rectangular box with here three inputs are provided. In the previous case for half adder we provided just two inputs, and you get the same two outputs, sum and the carry in the half adder also has the same as half adder. Now coming to the circuit diagram of full adder, we saw that sum is nothing but A XOR B XOR C. We could implement this with the AND and or gates or and NOT gates, but it would be a lengthy expression, so I just used XOR gates directly. You pass your two inputs for XOR and you get here A XOR B. Now you pass another input C to it and you get the sum expression. In the same way, you could this is not like you see the expression, right? This is nothing but AB plus BC plus CA, which you saw in the previous case. This is nothing, just nothing but the distributive law. You provide the three inputs A and B, two inputs A and B to the OR gate, sorry, AND gate, and you provide again two inputs to the other one. Now you get here the same output AB plus C input, which is the same case as AB plus BC plus CA. Hope you understood this. And coming to the applications of adders, it's useful in many areas. Like first of all, it's used in arithmetic logic units. Like previously I told you, it's used in addition of single bit binary numbers. Full adders are useful in also useful in adding two-bit binary numbers, which will be too complex to explain now. Core components in microprocessors. It's used in core components in microprocessors so that they're useful in signal transmissions and calculations for the additions. In binary addition in calculators and digital systems, it's very useful in binary addition and which we discussed in the whole presentation. Multiple addition to cascading full adders, which I was telling in ALUs. You could add, like, see, here we are adding two single bit binary numbers A and B, and you get the sum and carry. Or three inputs, you get the sum and carry. But when you wanted to add like something like AB is single two-bit binary number and CD is another two-bit binary number. When you want to add this, it's possible using the full adders. You cascading full adders is nothing but you place two or three or four of them and give output of one of them to input as other one or do some logical expressions and you get the output, which would be addition of multi-bit addition numbers. Coming to the conclusion, I want to conclude this by telling that adders are essential in digital electronics for arithmetic computations, which we discussed in this whole presentation. Half adders can add basic operations, while full adders are suited for more complex tasks, which is nothing but in the previous case. You can add multi-bit numbers, which is very useful in the digital systems. If you have any questions to ask or provide feedback to me, you can feel free to provide it. Thank you all for providing me this opportunity. I hope you understood in detail about half adder and full adder. If you have any doubts, you can feel free to ask me. Thank you.